Thanks, Itai. And now I'm not going to do something. I'm just going to talk. So I'm happy to be here. I'm honored to meet so many people who are involved in Unix, and so it's a real honor. But I'm going to talk about Unix and robotics, and I'll start with my takeaway messages. Yesterday, hardly any robots ran Unix, and my sort of guess, order of magnitude, is approximately, this is order of magnitude, approximately one robot in 1987 was built on Unix, tens of them by 1997, and thousands by 2007. Today, millions of robots run a version of Unix. It's millions. And my guess, it's hard to say how many robots there are in the world by different counts, that perhaps 2 million of the 30 or 40 million robots in the world use Unix today. But all the trends say that tomorrow most robots will run Unix. There will be holdouts for some reasons, and I'm going to talk about that. But what I'm going to start off with is talking about why it took so long for robots to use Unix. But first, what is a robot? And there's many definitions. We sort of know these factory robots. We've had them for a long time, and I'll talk about their beginnings. Robots, in automobile factories is what the Robot Industry Association used to say robots were until fairly recently. There's only a few 100,000 of them in the world. So these are the robots that populate factories, and there are no people next to them. They're all robots, no people, and I tried to fix that and made some progress over the last few years. But then there's also been robot toys. Furby was a didn't have much of an actuator. Pleo up there on the left was could move around and make noise. And I'll show you my real baby, which is a robot toy that I built. One of the 14 failed business models. It's not actually a real baby, but that's another. And then there's robot vacuum cleaners. iRobot has about 60% of the world market for them. But there's also military robots, and iRobot was part of that. We had robots in Afghanistan and Iraq doing roadside bombs. And then another one of our failed business models at iRobot was actually nuclear power plant inspection robots. We had done that in the 90s, and then on March 18th, 2011, sorry, I was going to talk about cars. I've lost, I'll come back to that other story in a second. Cars are becoming robots. Right now we have lots of sensing, and the actuation is largely via the person, via beeps telling them what to do. But self-driving cars, they're robots. They're not going to be here as soon as everyone thinks. They're not going to be one-for-one replacements with existing cars on roads, but we will re-engineer our cities over the next 30 years and gradually introduce them into our cities. So 30 or 40 years from now, there'll be lots of self-driving individual robotic devices moving us around with re-engineered roads. This is one of the few deployments right now. This is May Mobility that deployed in a few cities, but every single deployment in the world as of today has a courtesy driver in them, in case you don't know. There's a courtesy driver. And then the other sorts of robots that I've seen a lot of recently, have been drones, and they're a special class, and I'll talk about them. The reason I just got confused about the order in this talk, this is a brand new talk. I've never shown any of these slides before, so I'm not quite synced up. Now, to understand what is hard about robots and why it took a long time for Unix to get to them, we have to go back to the old days, olden days. So the very first industrial robots were Unimates. They were in a GM factory in Trenton, New Jersey. There was actually the first prototype, it was 001, was there in 1959. This is the Unimate 1900 series. I don't know how they got from 001 to 1900 series, but they did. And these were started to be deployed in GM here in New Jersey in 1961. And they were used for picking up castings. So there was, the hot things that people had to pick up, castings. Now, this was a Joe Engelberger. George Duval had the basic patent. Joe Engelberger was the business guy who made this happen. And I get really annoyed with some of the press about robots today and some of the hype. Well, here's Joe with Johnny Carson in 1965, and he's the Unimate 1900 has a baton, and it did this and got the Johnny Carson Orchestra to, conducted the orchestra. He also had it pour a beer, and of course it couldn't really do all this stuff, but he did that. But this was part of, by 1965 he had about 450 of these robots out there, and he wanted to go international, so this was part of his international expansion. And he went out internationally and signed up some companies that actually licensed and built them. And Marcus, what do you think the very first company was that Yes. You've probably never heard of it. No, I did. It's a little Finnish company.
Oh,
yeah, there it is. That was the very first company outside the US that licensed and built industrial robots. The second one was Kawasaki Heavy Industries. They still have Kawasaki Robotics. Showmanship works sometimes, unfortunately. Now, that robot did not use a computer even, but I want to give you a reason why that was. And I just want to compare the PDP-7, which was 1969, $72,000 for the PDP-7. There were only 120 of them built, it turns out. They were wire-wrapped. And that means no factory floors for you, because they would have just gotten dirt in them, shaken, and it would not have been possible. And it was an 18-bit word machine, 4K to 64K words. I don't know what size the one that was used here that was for the first Unix. It weighed 1,100 pounds, but it was 4 microseconds for a standalone 18-bit fixed-point add instruction. And you got to decorate that around. Now, what robots needed was something much cheaper than $72,000. You weren't saving much money if you had to have a computer of that price. It needed to be mass-produced, needed to sit on the factory floor, and you needed to do more than 100,000 floating point operations per second, even for a pretty primitive robot. And I'll explain why that's true. So the early robots didn't even use digital, they used analog circuits. They weren't very flexible as a result. They were sort of pretty cruddy control systems, which is why just picking up a casting was something they could do. By the way, Unix had no real-time guarantees, and that was a big problem. So I'm going to go through now, just for a few minutes, just to show you how scary the amount of computation you need to move a robot around is. Just not even sensing the world, but just sensing itself. So there's going to be a lot of equations, but you don't have to understand them. They're here to scare you. That's the purpose of this. And I'm not even going to show you, oh, yeah, for a real robot to do something in a factory, you really need 6-dimensional coordinates, because, if you want to grab something, there's the X, Y, Z to get to a place, and then there's 3 more coordinates for the orientation. Think about on the surface of a sphere, pointing your thumb, that's 2 degrees of freedom, 2 orientations, and then what the twist is on the surface of the sphere. So that's 3 orientations, 3 X, Y, Z. So you really need 6 degrees of freedom. You need 6 different motors. And these factories, or these robots, largely have, see, I'm just not up with it. They largely have 6 axes, 6 motors. They're not in the X, Y, Z coordinate system. They're in a different coordinate system. They're just rotating joints. So you've got to get from there to where you want to be in the world. And I'm going to, and that's one sort. This is another sort. This is the Puma, which I'll come back to in a minute, which is a very popular version of the Unimate that eventually came from that same company that Engelberger had started, although this was developed by Vic Scheinman out at Stanford and then bought by Unimate. So this is what robot arms look like, typically 6 degrees of freedom. And what we're going to glance at now is forward kinematics, inverse kinematics, trajectory control, and how to apply desired forces, just to show you the mathematics. But 6 dimensions is way too scary. I want to scare you with equations, but they're too scary in 6 dimensions. So I'm just going to go with 3 dimensions. I'm going to imagine a little robot that can turn in place, lift its elbow, and this is a shoulder, isn't it? Lift its shoulder and bend its elbow. And so I'm just going to get an x, y, z position for this endpoint with theta 1, theta 2, theta 3, the 3 angles. That's the forward kinematics where I'm going to go backwards for a second. The lengths, L1, L2, L3, are the lengths of the links, and then going forward now, C2, C sub 2 is the cosine of theta 2, S3 minus 2 is the sine of theta 3 minus theta 2. That's just all cosines and sines, a bunch of multipliers. That's the forward kinematics. If I know the angles of the arm, where's x, y, z? If I want to go the other way, I know where I want to be. How do I compute theta 1, theta 3, and theta 2? It's a more complex computation. Then if you want to follow a trajectory, well, you could just go to an XYZ, XYZ, XYZ position, but as you move between them, the joint angles will be traveling at maybe constant velocity, and you sort of get this sort of lumpy curve. So, well, we can fix that by using calculus and figure out how to control the velocity of the joints. And so you differentiate, you get something called the Jacobian, which is this matrix, which is a function of theta. You can see there's lots of computation. This isn't just in 3 rather than 6. And then you get the derivative of how you move it in terms of the derivative of the angles, and then you invert that, you invert the matrix, and you just get lots and lots of computation. And then that doesn't really control it. That just moves it to a place or moves it in a trajectory. But in fact, there's mass involved. So here's from my company. This is, let's start that video. This is Shiwei Wang, one of the engineers. And here we've got the robot applying 0 force to its endpoint in real time. So she can just touch it and move it around because it's sensing the force that she's applying, and it's trying to zero it out. So this is what you need for a robot that's going to be safe to interact with people or do insertions, as you might want to do, as people do to plug things in or do stuff. And that gets way harder than what I've shown you for the kinematics. Even 3 dimensions is too scary. So I'm just going to show you 2 dimensions. I'm not going to go through the details, but even the simplest version of dynamics and torque gets you way more equations. And so you just got to be computing all the time. You got to do this about 60 times a second. So it's just a load of computation to do anything. Equations after equations after equations. This is what we taught in robotics for 30 years. This lasted a whole semester to get a simple 6 degree of freedom arm. And then, this is from a 1992 book, people were counting how many additions and how many multiplications needed to be done. And it turns out to be a lot when you multiply those by 60 times a second. So computers just weren't enough to do this for a long time. And when they were enough, you had to have a cheap one. So you couldn't waste any cycles on anything except this arithmetic. Couldn't have one of those operating systems around. It was just, so we didn't have operating systems. We just had bare metal doing these computations. And there's multiple solutions. So until relatively recently, commercial robot arms needed every ounce of computation just to move around, let alone doing anything smart. And there were hard real-time constraints. You had to get those numbers there at the right time, had to do it. So robot arm companies have used embedded processors with fixed processing loops, and still today, the vast majority of robot arms are programmed this way. They're not very interesting from a computational point of view. But there were some early Unix heroes, and they were at Bell Labs Home Dell. I don't know if people are aware of this. I don't know if any of the authors of this paper are looking in, Bob Gaglianello and Howard Katzeff. Does anyone know them? Are they here? Is that you? Is it? Okay. So they, in 1986, had this paper about a thing called MegaLoss, a multiprocessor operating system, and for real-time applications. It was a Unix on a DEC VAX with a whole bunch of Motorola 68000s. And the Motorola 68000 was the processor used on the original Macintosh. I think it was, by the time we got to Sun Microsystems, maybe in a 68010 or a 68020, I can't quite remember. They had low latency, 750 microsecond communication between these 68000s. So it was a 32-bit VAX, it's in the paper, it says the Unix extended kernel, and the satellites were controlled by the VAX, the 68000s. The Unix handled all the file I/O, 80 megabit per second network between them, and they used at most once semantics. So it was just do this, but only do it once, and that's important. We'll get back to that. The satellite processors were up to 12 68000s. They're a 32-bit machine. The originals had a 16-bit memory channel. I wrote so many compilers for this machine back in the day, so I know it well. But even though it was a 16 megahertz machine, the division instruction took 10 microseconds still. So it was still pretty damn slow. And that was for a fixed point, let alone floating point. But they had real-time guarantees in this sort of Unixy kernel that they had running on each of the 68000s, and then they had pipes between them. So it was a Unix environment for programs there. And some of them, the 68020s, had a floating point unit on board, which meant you could start to do some computation. But they needed a whole bunch of them, 12 of them, to do enough computation to do something interesting. On the VAX, there was no support for security, failure handling, or availability. So this was not a commercial system at all. It was a research lab. And then Russell Anderson at Holmdel built a ping pong playing robot using MegaLoss. Did you guys see that? Did you guys? Yeah. So Russ was a member of technical staff at Holmdel. He received a PhD for this work, working with Lou Paul and Rosena Baici at Penn, and I was the external reader on his thesis. So all I did was correct his English and stuff like that. But at least I was aware of it. So he had a MegaLoss system, and then with Neil Westey's group at Holmdel, or I'm not sure where Neil Westey was, they built a custom chip with 10,000 transistors to do, because even with all that computation, they couldn't do the perception in real time. So they built a custom chip which got a center of mass of a white blob, ping pong, white blob. And they had 6 of those chips on each vision board, and they had multiple vision boards. This was an amazing tour de force. And even worse, they had a rolling shutter camera, not because they wanted a rolling shutter camera. A rolling shutter camera is that when you take an image, you're getting the image at the top at an earlier time than the image at the bottom. So it's smeared out in time. And he's trying to watch ping pong balls. And so he had to compensate for that rolling shutter, along with all the other computation. And he put it on this commercial Puma robot. I showed you the 560 version. He had the 260, a smaller one. And he played ping pong with it. I'll start this up. There's a bit of a lag as it enters. So this is Russ. This is Russ himself playing ping pong. You notice he's got black gloves on so that only the ping pong ball shows up in the cameras. You see above there, you can see some stereo cameras. On the left is the custom vision hardware. On the right, I believe, is the MegaLoss system with the 68000s, and there's a VAX controlling them. And this was able to play ping pong in 1987. Last year, KUKA came out and said, we have a robot that can play ping pong, aren't we fantastic? And I said, well, it's 30 years late, guys. And in a minute, you'll see some of the images of the ping pong ball. He had to correct for where the ball was, and then from the trajectory, he was estimating the spin on the ball, and then estimating how the ball would bounce once it hit the table. I mean, this was just amazing stuff that he could do. Just a second more. I'm not real good at editing videos, so now you see the ping pong ball going and it's showing up on the screen, the trajectories. He's predicting the bounce, and then
ping pong is being played by the first robot in the world that is fast enough to play against a human.
Yeah,
the robot was built.
Yeah. So the important thing there really, and this is where it leads to with Unix today on robots, is this most wants semantics. Not trying to shake hands back and forth. Let the real-time stuff happen by itself and just give it advice occasionally. That's a really important aspect of architecture for robots today. Now, I was a researcher at MIT. You know, we were just these poor country bumpkins compared to Bell Labs. Bell Labs could have real hardware. We had to scrape everything together. We didn't even have shoes. It was terrible. Oh my God. So this is what non-Bell Labs was like at the time. This is the robot Genghis, which was in the Smithsonian for many years because it led to the rovers on Mars. But you know, I used 4 8-bit. This is 1988, the year after Russ. 4 8-bit Hitachi processors with a total over the 4 of them of a kilobyte of RAM. You know, I had to make the token ring out of serial ports, and just with 2 8-bit ports, servoed the motors. And so Genghis was able to walk over naturally occurring rough terrain that was found in my lab, sensing everything with the whiskers, lifting its legs higher when it needed to. So not much computation. And then during the 90s, computation became more. So this is Kismet, a robot that Cynthia Brazil built during the 90s. And we had 100 megahertz PCs by that time, a few of them. We had 68070s running in Lisp, running the real-time stuff. But we had to build it by hand. I'll just show you what we could do in the 90s with that. This is, oh, no, let's go back. Sorry, I didn't quite want to start. Okay, I'll tell you when to start the video. Here we got people off the street who didn't know what was going on and told them to talk to this robot. The robot did not understand English. It did understand the prosody in people's voices. And it didn't speak English, it spoke English phonemes and put prosody into them. And so then we'd watch people interact with the robot. So now let's run this. This is Richie. Yeah.
Let's run this.
Yeah, I want to show you something. This is a watch that my girlfriend gave me.
It's doing motion detection.
Yeah,
it's according to the motion. So he thinks it understands. It doesn't understand. But I liken this conversation to being in a bar at 2 a.m. You're both sort of talking. You don't really know what's going on. Neither side. It's not real communication, but it sort of feels like it. Anyway, that's what we were doing then. But to try to commercialize that was much harder. And this other robot that we had, COG, by this time we could have it learning dynamics. Here, it's getting force feedback. You'll notice the high, the really great graphics that we have here in a second when we switch off the force feedback. Things were harder then, and now it can't feel that it's a crank. When we switch it back on, it feels that it's a crank. It doesn't know that it's a crank, but it feels that there's something there, and it gets into a rhythmic vibration. And then he comes and he adds masses to the arm, and that completely changes the dynamics, and it adapts to that. And this is the work of a lot of people. It was pretty hard to do. But we were starting to have, by then, frameworks for robotics. And in my lab, we had one called YARP, not yet another compiler, but yet another robot platform. Thank you for that idea of how to call them. And so people were starting to have software platforms for robotics, but built on real-time operating systems still. So the real-time operating systems are things like RTX, VRTX, and Nucleus, RTOS, real-time operating system, which is POSIX compatible, but it was a real-time version built commercially. And then when we started by that time to have two classes of processors, computation was getting cheaper. We had small embedded processors for real-time direct motor and sensor control, and a master processor running a real-time operating system for high-level processes and communication between them. And it was a bit like MegaLoss that was developed here at Bell Labs, but still a real-time kernel. But outside the labs, we didn't have that at all. Toys and consumer robots were driven by low price. So there was almost no computation that you could afford to put in a consumer robot. And so it was really hardcore embedded. And one of the things I contributed to these sorts of robots, I was always in Asia with my job with MIT, talking to people for research, and I would go off on little side trips to Hsinchu in Taiwan, where TSMC, Taiwan Semiconductor Manufacturing Corporation is, lots of little companies using that fab facility. I'd go from company to company, little company, and find out what processes, little tiny cheap processes they had, and figure out whether they were good enough for what we wanted to do. So this was a robot doll that we produced at one of the failed business models at iRobot, so-called My Real Baby. There's Clara Vu. She started out with me as an intern from Yale, and we networked stripped down 6502s. 6502s were in Apple IIs. Some of the Taiwan-based companies had stripped them down, got rid of a lot of useless instructions, made it less silicon, and so we had two of them on this doll, on this consumer product. And we had a network between them, 128 bytes of RAM, 50 threads running on 128 bytes of RAM with a 4 bits per thread status.
My real baby, and she's sleeping right now.
So
pick her up.
One motor to drive the face. People thought it was a little bit like Chucky in the, you know.
You can play with her.
And sensors on its foot, and it faked peeing, and we had to change its diaper and stuff like that. It was a failed business model.
Really ticklish.
The first home robots were completely driven by price. This is a prototype that we had built for a vacuum cleaner robot in 1992, and that had lots of it had multiple chips on it because it was a prototype. But when we wanted to bring something out commercially, we really had to reduce the price. We had gone around and asked people how much they could spend without their spouse getting really angry at them. And the answer was $200, so that's what we came out with, which meant we had almost no budget. That meant cost of goods sold was about $50, so we had almost no budget for computation. And it took a long time to become useful, really, as robots, but we brought it out in 2002, and I had found a chip with 512 bytes of RAM that we could afford. That was luxury, I tell you. It was just great. So that was what commercial was doing, even as late as 2002. You could hardly afford any computation, which is sort of hard to imagine, but that was just the realities of embedded systems. And RAM was really expensive still on a chip, on a single chip at that point. But today, millions of robots run a version of Unix. How did that happen? How did we get from there, back in 2002, to here today? It's been quite a change just in the last decade and a half. And a lot of people say, is it ROS, the robot operating system? Robot operating system is very popular, but there's some things to know about it. The big thing to know about ROS, the robot operating system, is it's not an operating system. It's a layer of libraries, this is what ROS actually says on their homepage. It's a set of software libraries and tools that help you build robot applications, from drivers, powerful developer tools, etc. And it's all open source. And in the robot lab yesterday in the tour, those robots were running ROS. The students are using ROS. It's become very popular. First, it became popular in academia, and now it's trickling out into real-world applications. But the second thing to know about ROS is It's not even close to being the first such framework. It's the winning framework. It wasn't the first one by any means. There were lots of them over time. You know, I used to view it as my job at both MIT and at iRobot to keep whacking engineers and stopping them from building yet another new general purpose framework that everyone was going to use, because they kept doing it again and again. YARP, the one that was done in my lab, currently powers a lot of research in Europe with the iCub. I just looked on GitHub. The latest version of this came out just a month ago. There have been patches in the last month. So there's active other platforms. But all of them, pretty much these days, run on top of Unix. Usually Ubuntu is what they run on. So they're starting to be Unix-based robots. And this is that earlier part of the talk. Here's what I'm most proud of in my life. We had these robots that were used in Afghanistan and Iraq, and the pride will come in a second. The particular framework we used on them was called Mobility, ran above Linux, dedicated motor control boards. And we could do that early, back in 2002, 2003, for two reasons. One, they were military robots, so they could be expensive, relatively speaking, to consumer robots. And the ARM was teleoped and moved 100 times slower than in a factory. So we didn't need as much computation real time. One of our failed business models at iRobot had been nuclear power plant inspection robots. Failed in the mid-90s, but then March 18th, 2011, 7 days after the Great Tsunami, we got a call, can you get robots into Japan, into Fukushima? And we trained up TEPCO, Tokyo Electric Power Company, and then we had robots in the power plant shutting it down because it was a totally analog power plant system, no digital controls. It was a 40-year-old GE power plant. There were just dials, and no one could get out to see what was in the dials. No one could see what the pressure was in those buildings. So we had multiple of these robots go off and make Wi-Fi hotspots and get digital out into the high radiation areas, then put a camera on a pressure dial and feed that back so that people then had some information on what was going on, and then the robots were able to operate certain things out there under teleop control and shut down the power plant. I went to Fukushima 3 years later. It's quite, that was a very sobering day for me to go into Fukushima. It's quite a thing. Don't build power plants without digital channels. Don't build it where there's going to be a tsunami. A lot of lessons. But now, despite different versions, ROS is really ascendant. It's still not an operating system, still runs on Ubuntu mostly, but it's the system of choice for research labs everywhere. There are still some research groups running other legacy systems, but a lot of autonomous driving systems are now relying on ROS because they came out of universities which were using ROS. And ROS is also penetrating the industrial robot market and the high-end consumer market. And let me show you, and running on Unix. So here's Universal Robots. It's a Danish company, now owned by Teradyne in Boston, which is one of the fastest growing industrial robot companies. It runs Unix with ROS sitting on top of it. My own company, which ended up failing, we ran ROS on Ubuntu, and no, we don't need the music. Total artistic success, this company, commercial failure, although just on Monday, the people who bought the assets announced a new model of our robot coming out. This is Sawyer. They announced Sawyer Black, so I think they're going to paint it black instead of red. It's built in Germany. But this is a sort of force-controlled things that our robots were doing. And then a complete rethink of how you program robots instead of writing essentially scripts in a version of Pascal, which is a lot of commercial robots, how they're programmed. We did teach by demonstration, which builds automatically a behavior tree. Itai referred to behavior trees as what runs video games. So we thought, well, a lot of people know how to program behavior trees. This is a good thing to use to program robots. And this is This was a marketing video from Rethink Robotics before it crashed, and this is the trees that automatically get built. And along in the way here, you'll see that we could control not only our own robots, but lots of other company robots. So some of the commercial robots that were out there, in particular, somewhere you'll see KUKA robots here being controlled by our system, which used to run, these embedded hardcore systems. We just got them to run under ROS running on Unix. I think anyway, it's a modern user interface, using Node.js and all the JavaScript sorts of things that you use for a modern user interface. I'm going to skip over that. But one of the important things was we're able to sense forces in real time. This is something you couldn't used to do at all. So you can see there the circles showing how big the force is on each of the joints. The ones that are just rotary here don't have much force because they don't have to compensate for gravity. The big one at the top has to hold up the arm, so there's gravity. It's fighting gravity there, which is why there's so much force on it. And then these could be used to do all sorts of things the way people would do them, that if you just had a robot trying to do things by position, it had to be so precise, but by feeling forces, going until you feel the force, and then twisting and pushing, that's how a human would put that memory module in. There it's trying to click it in, there's a little, but it didn't have enough force, it failed, so it can measure when it's failing. Now you'll see it do it correctly, feel the force as it clicks, and so all is good. And totally safe for kids even. This is, just bringing kids into our company, and we didn't show them how to program the robot. They all figured it out just by looking at they knew how to use a modern user interface and pretty soon had the robot doing things, but safe to interact with. Now, why can we do this today when Ubuntu is not real time? Ubuntu doesn't give real-time guarantees. So what we do, and what all the companies do, is we make use of multi-core, and we lock certain threads down on a particular core. And it's not real-time guaranteed, but it's good enough. And so you run maybe a 200 hertz loop there doing the dynamics and trajectory planning, all those floating point computations you saw before, in that thread on that core, and let the rest of the stuff happen on other cores. And there you don't have, there's no real-time guarantee, but there's real-time comfort on that core. Don't worry, this is what your life is going to be like. You're going to, especially when you get older, these are the robots that are going to be getting you into and out of bed. It's fine, really. And then you have position and force control loops running at embedded processors right next to the motors at 1 kilohertz or 2 kilohertz. And these days, you then actually even do the commutation of the brushless DC motors and determine the current at 30 kilohertz. As the motor is turning, you change the current in the coils. So you have a 30 kilohertz loop running down in these embedded processors. So that's how we sort of separate out the real time from the non-real time, and it's sort of a cheat, but everyone's doing it, and it's good enough. And so it looks a lot like MegaLoss from 1987. But with this multi-core twist. And that is why Unix is now becoming the drug of choice for robots. The higher-end Roombas now all run on Linux. We used to have simple model names. Now the M6, the S9, and the i7 all run a version of Linux. They're on 32-bit ARM processors now, so there's enough oomph there to do stuff with multi-core. Everything's got more, vacuuming used to be easy. I like to say, I started off life with a degree in pure mathematics, and I ended up as a vacuum cleaner salesman. Who knows how life's going to turn out? And then most of the self-driving cars will run Linux with ROS. That's just going to be that future. Now, drones, on the other hand, have a lot of mass and power requirements. So what is happening is that the flight software stack is still running fully embedded, and then you can buy these add-on little Unix boxes, which people who have particular applications want to do some simultaneous localization and mapping with vision, etc., put on their drones. So there's because of battery life, some people don't want them on, some people do want them on. So that's, you know, an option, and the stuff you buy initially doesn't have Unix running on it. So low cost and low power and ultra high performance applications are going to be resistant to Unix, but most of the world can be sort of shoehorned in to run on it. And so that's why I say tomorrow most of our robots will be running Unix, and everything's going to be great. So thank you, guys.